Welcome everyone. My name is Eric Normand, and today I'm going to talk about functional programming and how you can use it to improve testing, reuse, and maintenance in your existing code base, regardless of if you're using a functional programming language. This should apply no matter what. Okay, so today I hope you come away with a new perspective on programming that you can apply to your code, new skills for writing better software, and some curiosity to seek out more. You know, this is only an hour, and so there's no way I could give you everything that there is about functional programming, but I hope that it inspires you to go find some more. So I'd like to start with a little story. Back in 2013, I started a meetup all about functional programming with some friends here in town, and every week, it was monthly, every month, the discussion would always go to one of these basic questions about functional programming. The big one was, what is functional programming? Because we'd have new people coming in all the time. They were curious. And so that was a big, like almost every time we talked about what is functional programming. They also had questions like, why should I care? Like, I already know how to program. How will this help me? Another question was, should I just rewrite everything in FP? Like, is this an all or nothing thing? Another question was, well, I already know JavaScript. Can I just do FP in JavaScript? Or for that matter, can I learn FP in JavaScript without having to learn a new language? And after these discussions, I felt like I had a pretty good grasp on at least what I thought was important to explain to people and to be able to, to teach what we did as functional programmers. I've been programming in functional languages for about 20 years now, and it's not a very common thing, and so I need a lot of explanation. And people would ask me, what should I read? What should I go do? And I could not recommend a book. So I had to write it myself. And the book is Grokking Simplicity. It is published by Manning, as you probably guessed. There's a coupon code if you would like to buy it on the Manning site. You'll get 40% off. Just use that link and that coupon code when you check out. So Grokking Simplicity is my attempt to take this idea of functional programming that's been kind of stuck in academia, at least in terms of how it's discussed in books, and give it to people from a perspective of practical commercial software, not academia. And to do that, I had to come up with a perspective on it that would allow me to teach it because I can't teach the whole thing. So I eventually wound up looking at functional programming as a set of skills. So if you look at this Venn diagram, on the left, we have this orange circle that is things non-functional programmers do. And then the circle on the right is the things functional programmers do. So these are different skill sets. There's a lot of overlap. A lot of the stuff that functional programmers do, you'll do, everyone will do. But then there's some difference. And that difference is what needs teaching. And so that's what I focused on in the book. These are the things that professional functional programmers do that other non-functional programmers don't do. All right, and then I had to come up with a linear order and a kind of organization scheme for how this is going to work. So I've discovered that there's really two levels. These levels kind of correspond to your level as a programmer, but because the second level requires the first one in certain ways, and the first one is actually necessary for the paradigm. So we're going to start there. We're going to go over both of these two levels There's two parts of the book that correspond to the two levels. And we're going to start with the first one. So part one is all about distinguishing actions, calculations, and data. To my mind, this is a fundamental difference in functional programming versus other ways of programming. Functional programmers distinguish these three categories. So we're going to go over what each of them is, and then the next bullet, we're going to look at how actions kind of spread through our code. And then lastly, we're going to do a refactoring to extract out a calculation from an action. So let's get started with distinguishing actions, calculations, and data. So we can imagine a code base, and we pluck some code out of that code base, and we'll see stuff like this. So the first thing is a little bit of JSON. It turns out to be a JSON object. Then there's this function called send email. There's a function called sum. There's save user DB, string length, get current time, and then this array of numbers. Now I've starred three of these functions because they're different from the others in that it matters very much how many times I call them or when I call them. So for instance, send email, if I call that 2 times, the email is going to get sent twice. And I don't want that to happen. So I put a star next to it just to indicate it's different. Whereas if I have sum, I can sum the numbers as many times as I want. It's not going to affect the outside world, right? So you can imagine how send email would be harder to test because you might want to run send email 20 times to run 20 different tests. And now you have to deal with, am I actually sending these emails? Likewise, save user DB. It depends. If you call it 0 times, it's very different from calling it 1 time. And then get current time. Every time you call it, it's going to give you a different time. So this is these all get a star. They depend on when they are run or how many times they're run. So functional programmers will put all those starred functions above the line, and we'll call those actions. Okay, that's the term I came up with that I'm using in these slides and in my book. We'll talk about what functional programmers generally call these later, but we'll call them actions for now. So now there's everything else under the line, and there's a difference between just bits of data and a function that you can run. So we'll draw another line. So the below the line will be data, and then above that line between actions and data is calculations. So calculations are actually things that you can run. They're functions or operations, operators like addition or multiplication that don't have an effect on the outside world. They're just computations. And then the data are inert things. So let's go over each one and give precise definitions. So actions, if you look it up in the dictionary, one definition you might find is the process of doing something typically to achieve an aim. And I think that captures what actions are all about. They're trying to do something external. It's not just thinking about it, it's actually doing the thing. We call them in FP jargon, you might have heard these terms before, impure functions, effects, or side effects. So these are the terms that you'll hear outside of these slides in my book. I use the term actions because I think that these are misleading and confusing when you're a beginner. So for instance, function is both a mathematical concept and a language feature, and they're different. And then effect, it's not a great term because it's actually we're talking about the cause. So the cause of the email being sent is the function that's called send email. The effect is the actual email that arrives in your inbox, right? So it's not quite the effect, it's the cause, but then cause isn't the right word either. Okay, so I had to come up with my own term. Okay, and then there is a rule of thumb for identifying them. Actions depend on when you run them or how many times you run them. When you run them, that's like the order that you run the actions in. And then how many times you run them, that's repetition. So if you call it 0 times, 1 time, 2 times, what happens there? Okay, next we have calculations. Dictionary definition is computation from inputs to outputs. These are, in FP jargon, we're going to call them pure functions or referentially transparent functions. Again, it's problematic because in a lot of languages, they are not implemented as functions. I mentioned before the addition operator, plus, times, divide. Those are calculations. They are pure. They don't have any side effects. They're not actions, but they're not functions either. So I came up with this term, calculations. And they are eternal, outside of time. I mean, imagine addition. It's never going to change. Any machine you run addition on, it's going to give you the same answer forever. You know, you can't imagine it changing. If it does change, we'll be in big trouble. Okay, data. Facts about events used as a basis for reasoning, discussion, or calculation. So data is kind of the most boring of them because they're inert, but I think they're actually quite interesting in themselves. They're serializable, they're self-identical, meaning they are what they are, which is kind of interesting. You know, a function is kind of opaque. You don't know what it's going to do really until you call it, whereas data, you can read it. But the downside of data is that they require interpretation. So you need software to parse it and make assumptions about what it means in order to use the data. So we're going to talk mostly about actions and calculations because data is there's not as much to say. And the big distinction is when you're writing code. So the thing is, functional programmers tried to write way more calculations than actions. Like more code should be in your calculations than actions. Basically as much as possible in calculations, actions only when necessary. Why? Because actions depend on time and it's just a pain to work with. They're much harder to deal with, as we'll see. The thing is, though, that we pay much more attention to actions. We spend more time with actions because they are harder to work with. And this is kind of a common misconception in functional programming, that we don't want to use actions at all, or that we basically try to ignore them. We actually spend a lot more time and a lot more attention making sure that our actions run correctly. And I think we spend it more than other paradigms. So it's kind of interesting that there's that kind of duality. We spend more code on calculations, but then more attention on actions to make sure they're right. All right, we're going to talk about the spreading rule. So let's imagine this programmer has some code and she can correctly identify that this function called send payout is an action. We should go through what the code does. So down at the bottom, there's the main function, and it calls affiliate payout with the affiliates. Affiliate payout is going to loop through all the affiliates and then call figure payout for each one. And figure payout is going to multiply the sales from the affiliate times the commission. And if they're owed more than $100, it's going to send the payout, meaning it's going to contact the bank and transfer money to their account. So obviously send payout is an action. It's physically or it's reaching out to another system and sending money to them. So if you call it twice, it's a big deal. You're giving too much money. But is the rest of her code actions? She claims it's only got this one. So let's apply the spreading rule, and we'll learn it as we go. So we'll start with that one highlighted action. Now, one rule of the spreading rule, or one part of the spreading rule, is that a function that calls an action must itself be an action. Because now if I call figure payout twice, well, that's going to send the payouts twice too. So figure payout also is an action. And because that's an action, we have to highlight the place where it is called in the next function. But again, we can continue, recursively applying this rule. Oh, sorry, you can't read that down there. We can continue recursively calling this rule. And of course, affiliate payout is an action because it called the action. And so now we have to highlight affiliate payout in main. And then, all right, now main is an action and nothing calls main, so we're done. But the thing is, it's all actions. You have actions at the bottom of your call stack, the top of your call stack. Everything under that, all the way to main, is going to be actions. And so this is one of the problems that functional programmers have recognized in using actions in like anywhere in the code, is that they spread. They just spread all up until main. So you're going to have actions in your code. We need to send that email. Like that's what the software is supposed to do. We need to send payouts, but we just have to identify and be conscious and mindful of what is an action. So this spreading rule helps us see that, yes, if you put action somewhere in there, it could spread all the way and infect everything. Okay, we'll talk about the problems with actions in a moment. First, let's talk about extracting calculations. So this is here, I'm going to turn my video back on. This is a refactoring that will let us take some existing code that's a mixture of actions and calculations. Maybe it's one big action, and extract out a piece of it that could be a calculation. So here's a function called showTotal. It initializes total to 0. Then it loops through the items in a for loop. Right, items is some global variable somewhere. And it's going to add the price of each item to the total. And then at the end, it's going to set the inner HTML property of this DOM element to total. So it will show it in the web page. All right, so we can deduce a couple things. The first is that the red elements are actions. So let's start with items. So we're reading the value of a global variable. And a global variable could change at any time, right? We don't, calling showTotal when the items has 20 things in it is going to be different from calling it when items has 10 things in it, right? So now showTotal depends on when it is called because it is reading items. Likewise, it is setting something in the DOM. So if we call it again, I mean, maybe this wouldn't change the DOM because you'll get the same total calling it 2 times. But if we called it 0 times versus calling it 1 time, that would definitely be a difference. So that part is an action. But I've highlighted in blue all of this other stuff that's not really an action in here. So this iteration through the items array and updating total, adding to total, like all that stuff it's going to give you the same answer. If items were the same, this total is always going to be the same. So we can probably look at this blue stuff and try to extract that out as a calculation. So we do that. We make a function called SumTotal, and it takes items as an argument. And then we have this for loop in there. Now items in here is blue because it's the argument. Once it's passed in, it's not going to change. Because, you know, we can, if we need to sum a different array, we can just pass it in. We don't have to assign it to a global variable. And then it's going to return the total at the end. And now show total, instead of having the for loop in line in there, it's going to call sum total. And I made a mistake. Items should be red because it is still reading from the global variable. So this items thing should be red. And then of course this is unchanged. So notice we've built a calculation called SumTotal. We've moved a lot of code out of this action and into a calculation. Now let's go a little bit deeper in what we actually did here. These two reads to items, these are actually implicit inputs to our function. They're implicit. The explicit inputs to a function are the arguments. But these are implicit inputs. It's data entering the function that doesn't go through the arguments. And then we are setting the inner HTML property, modifying the DOM. That's an implicit output. The explicit output would be a return value from the function. So we have an implicit input and an implicit output. And we've replaced them with explicit inputs and explicit outputs, at least in our calculation, right? So this is the refactoring that we're trying to do. We're trying to identify how does data enter into the function, how does it leave, and only use arguments and return values to do that. And we could just write it out like this: replace implicit inputs with arguments and replace implicit outputs with return values. Okay, now let's talk about reuse, testing, and maintenance. So this, I'm just going to ask it like this, like, which is easier to reuse, calculations or actions? So when we're talking about reuse, we are talking about taking some code and using it in different departments, different run times. So meaning you could run it on the server in Node or in the browser, or, you know, what have you, depending on the language you're using, different contexts. So you could be running like this sum total to figure out the taxes that are required for those items, or you could be calculating the total to display into the DOM. Different assumptions, like you could be assuming that these items are actually in the shopping cart versus these are items in an inventory, and at different times. So you want your code that you write today to still work in a year. And so if you tie in if you have all these implicit inputs and implicit outputs, you're baking in all these assumptions about the context and the runtimes and who needs it for what purpose. And by separating it out and making it into arguments and return values, you're actually able to reuse it in different contexts, because it's so much easier to vary the inputs because they're just arguments, and use the outputs for different purposes because they're just return values. So I would argue, and I think most functional programmers would argue, that calculations are just inherently, by definition, easier to reuse. Which is easier to test, calculations or actions? So actions depend on how many times they are run and when they are run. And when we're testing our code, we usually want to test it more than once, right? So we might have 20, 100 tests to test one function. And so we're going to run that function 100 times. So we're already running it multiple times. And then, of course, we might run that function 100 times in one day. Every time we modify some code, we rerun our tests. And then when we deploy, we're going to run it on the build server. And then, of course, it's going to get run again in production. And so these are different places, different times, different run times. And, of course, we want our tests also to live on and be valid in a year so we don't have to keep writing them. So just by definition, I argue that calculations are easier to test. For instance, if you wanted to test our show total that modifies the DOM, you have to set up a DOM. Maybe you have to mock it. Maybe you have to always test that function in a browser that's going to have a DOM for you. And then you have to look into the DOM to see if it worked. So it's much harder to test than the sum total function that just has a return value. You can easily just look at that number, compare it to what you expect it to be, and have an easy test. All right, now which is easier to maintain? This one's a little harder because maintenance is more complex. But usually when we're talking about maintenance, we're talking about changing context, we're talking about changing assumptions, changing requirements, changing assumptions. Maybe we learn something new about how the domain is supposed to work. So when we're dealing with actions that have these implicit outputs and implicit inputs, those assumptions are baked into it about where the data is going to go, where it has to be used. And with a calculation, the assumptions are much fewer. Yes, you have to assume some things. Obviously, you have to assume this items that are being passed as an argument are in an array, right? Or they all have a price property. Yes, you have to assume that stuff. But you don't have to assume that it's in a global variable that has just been updated with the correct items, right? That's a bigger assumption. That kind of assumption ties that for loop into a particular order of things executing, and that's much harder to maintain. As more things are using and reading from that items global variable, you're just going to have a lot more trouble. So that sum total function is just so easy to just copy paste into a different context or import it and use it in a different context. So I'm just gonna, this one's harder to argue for, but I would argue that calculations are simply easier to maintain, almost by definition. Okay, there's much more in part one. I've just talked about 3 particular things. Part 1, we work with immutable data. We look at 2 major strategies for working with immutable data. One is called copy on write, and the other is called defensive copying. We talk about how to interoperate with non-functional code using the defensive copying. Sometimes you can't get rid of all the implicit inputs and outputs, but we do show how even getting rid of some of them improves your actions. Having an action that writes to the DOM, but it takes an argument instead of reading from a global variable, that's even better. We talk about dealing with state that changes over time. You still need state. Every application needs state. Functional programmers use state all the time. We're just more careful with it. And we talk about something called stratified design. This is kind of a design principle about structuring your code into layers. So there's a ton of stuff in part 1. It's about 7 chapters. So I couldn't possibly go over all of it here. So please check that out. I'm going to move on to the second level. So the first level was all about distinguishing actions, calculations, and data, and what's possible once you make that primary distinction that kind of defines functional programming. The second one is all about first class values, first class functions, and higher order functions. Once you realize that you can pass functions to other functions, return functions from functions, there's a lot of stuff you can do. We're going to talk about some of those now. So the first thing is, just to kind of get an idea of first class values, we're going to do a refactoring called express implicit argument. Then we're going to do a refactoring called replace body with callback. This one is about syntactic abstraction. And then we're going to look at how we manage the repetition of actions so that it doesn't interfere. All right, so first thing, refactoring is express implicit argument. All right, so refactorings kind of are answers to code smells. Code smell is a problem in your code that's not something that you can really put your finger on. It's not necessarily a problem, but sometimes it is a problem. So here is the implicit argument in function name smell. So let's imagine we had these three functions: set price by name, set quantity by name, and set discount by name. Let's look at the top one, set price by name. You notice that it gets something out of the cart by name, and then calls that item. Then it calls object set, which is a function that is going to update the property of that item. And what property? It's passing in the string price. So it's like the key. And then price is the value that it's going to set it to. Price is another argument. And then it's going to set in the cart the name to the updated item. Okay, now notice set quantity by name is very similar. The only difference is that set price by name uses a string price, and of course the argument is called price. And then set quantity by name has the string quantity, and quantity is the name of the argument. And I haven't written it out, but you can imagine that set discount by name is the same, except it's the string discount instead of quantity. So this is a smell. The code is very repeated. The only variations are, the significant variations are this string that's hard coded in there. And there's another aspect to it, which is that the name of the function, the part of the name at least, is kind of acting like an argument. It's an implicit argument. So price is matched with the string price, and quantity is matched with the string quantity, and discount is matched with the string discount. So there's a refactoring to make this argument a real argument, make it an explicit argument. So instead of just being in the name, we're going to use a more abstract term that can cover all the price, quantity, and discount. We're going to call it field. And notice we added an argument. And that argument is going to go in place of the string. Okay, I'm getting a question that what language is used in the book. I use JavaScript. It's a good question. I use JavaScript to be kind of a universal language. It is not, I have to emphasize this, it is not a functional programming in JavaScript book. I'm not recommending you do, that JavaScript is a great language for learning or doing functional programming in, but it is good for teaching functional programming basically because I have to teach so much. Whereas in other languages, let's say I chose Haskell, these would all seem like language features. Whereas in JavaScript, you can actually, show how to do it. So the language is JavaScript because most people can read JavaScript. If they know C or Java or C#, they can read enough JavaScript to make progress. Okay, so back to this. Field becomes an argument, and it's replacing that string. So now if we wanted to call set field by name, or if we wanted to call what we used to call set price by name, we would just call set field by name and pass in the string price. We can see that here. We are calling it with different strings, and now we don't need 3 functions that basically do the same thing. And what we're doing is making field a first class value. Before, it was not first class. It was just part of the function name, and now it's first class. So that means we can pass it around. We can maybe even concatenate it together to make a new field. There's so many possibilities because we can use the whole language to make that, to work with that value because it's first class. Now, if you were using TypeScript, I would suggest, making a type that knew all of these strings. If you're using Java, you might use an enum. I'm certainly suggesting to use the tools of your language to make this easier. But if you're not, you could still add something in here, like a validation, to check field against a list of strings that are allowed, right? So there's still room for safety there. And also, I don't think it's any less safe than the original JavaScript. You could have typos in the string and the function name, or in the string that gets passed in. So it's not like we've lost any safety there. Okay, next refactoring, replace body with callback. So here's the smell. We have these 2 for loops that are pretty much the same. They're just iterating through different arrays and doing different stuff inside the loop to each thing. So the first one is all about cooking and eating foods, right? It's looping through each food and cooking it and eating it. And then the last one, once you're done eating, you want to do the dishes. So you're going to wash, dry, and put away each dish, right? But the loops are basically the same. So that's the smell. The problem is we can't separate this curly brace here from the close curly brace. So we couldn't just say, like, take the top part, the first line, and then make a middle, like make that into one function, and then the middle part, make that into a second function, and then the last line, the closed curly brace, make that into a third function. And so we just call A, B, C, right? We can't do that because we can't syntactically separate the curly braces. And every language has stuff like this where you just, you surround stuff with syntax and you can't separate them. So how do we do this? Well, there's a refactoring called replace body with callback. We're going to name the parts. There's the before part, which is the for loop, like the meat of that for loop. There's the closing brace, that's the after. And inside, there's the body. So the before and after are red and the body is green. Okay, notice if we ignore the name of that array, the befores and the afters are the same. It's the body that's different. So we can make a function that has the before and after, but it gets passed in the f, the function, as the body. So the body can be whatever you need it to be. And of course, we're going to make array a more generic, we're going to make this variable a more generic name than foods because we don't know what we're going to call it on. An array is kind of, we know it's got to be an array. Oh, and sorry, this should be array.length now that I'm reading it. But the body gets passed in as f. So how do we use it? On the left, this is the original code. On the right, we see that we have a for each. We're calling for each, passing in the array of foods, and we're passing in a function that takes one food, cooks it, and eats it. And that function that cooks it and eats it, we see up here in the definition of for each, it's going to get called for each element of the array. Likewise, we can do the same for the dishes. And this lets us abstract over syntax. It lets us kind of frees us from writing for loops for the rest of our lives as programmers. And we can start building higher level abstractions. Something functional programmers do all the time. Okay, we're going to move on. Okay, so here's a problem. Actions depend on how many times they're called. That's just built into, whatever. Usually it's built into the language that you're using, that you call something twice, it gets run twice. That kind of makes sense. But sometimes we don't want that to happen. Here's an example. So we have this function called send welcome email, and it just contacts our email server and sends it. You don't need to see the code. Just imagine it sends this email through an email server. And of course, the programmers have written a nice warning. Only call this once. Otherwise, the customer will get 2 or more emails, which makes sense. But it's just a comment. It's not going to actually prevent this from getting called. What we're seeing is a conflict between the way JavaScript semantics work. You call a function twice, it runs twice. And what we actually want to happen, which is to only call this one time, no matter what. So we have a solution. Notice we're writing another higher order function. It's called once only, and it takes a function as an argument. That's what higher order function means. It takes a function as an argument, or it returns a function. So let's walk through how this works. So we have a variable called hasRun, and we initialize it to false. Now, once only is going to return a function, and that function is going to check if hasRun is false. If it's false, it's going to set it to true, and then it's going to return the function. So the first time it runs, hasRun is going to be false, and so it's going to call f. It returns the result of calling f, doesn't return f. Okay, sorry. So the first time this runs, it's going to return the result of calling f. So it's going to call it and return the return value. But the second time, hasRun is going to be true, and so this is going to get skipped. Okay? And so now we can define send welcome email as passing this function to only once. Right? This is the same code we had before, but now we're wrapping it in this only once. So now we can call send welcome email as many times as we want. If we call it 10 times, it will only run this email server.send one time. Now, this is very similar to what we did before, where we wrapped a function. When we did the for each, we are passing the function f into this loop so that it can get called for each item in the array. But in this case, f, we're expecting it to be an action and only call once, right? And so this way, we are modifying the time. We're modifying the model of time. Now the semantics for this function, if it's been passed through only once, is no matter how many times you call it, it's only going to send at most one email. So we've taken the existing model of time and made our own model of time. And this is something that functional programmers tend to do, is like rework how time works. And time has actually two components to them. It's got the repetition and the ordering. Repetition, very simply, is how many times it runs. There's different ways you might want to control it. We already looked at call at most once, right? But you might want to call at most n times. So instead of a Boolean that goes from false to true, you could count 0, 1, 2, 3, and if it gets to 10, you stop, right? You could make something like that. Also, this is something very useful on the web or other user interfaces. Multiple calls in quick succession result in only the last call happening. So an example of this is if I'm clicking add to cart, add to cart, add to cart, add to cart very quickly, each one of those is going to do some asynchronous activity, hit the server. They're going to come back in different orders, and they're all trying to calculate the total and then update the shopping cart's total in the DOM. Well, you only want to calculate the total for the last item added, not the first one, okay, maybe, but the middle ones, you don't really need them. So you could have a model, which we develop in the book, where only the last one gets run. Okay, so there's also ordering, which is basically when, because it's not about clock time, it's about when it happens relative to other things, which is just ordering. So one thing you might want is one action at a time. You don't care if A happens before B or B happens before A, but you want to make sure that they don't happen at the same time, right? So you can queue them up in some way so that only one happens. Another thing is you want one action to start after others finish. So you might have 10 asynchronous things that need to happen. They all gather these 10 things, up, and then you want to do something with all 10 of them at the same time. You might be familiar, if you're a JavaScript programmer, you might be familiar with promise.all. This is a way of doing that. But we develop a way also in the book. And then another one is effects happen in the same order as causes, right? If I'm adding stuff to the cart and then the AJAX requests happen in different orders, and so I see the shopping cart total of the third one when I've added 10 things. Like, you don't want that to happen. You want the last one, its effect of like writing to the DOM, you want that to happen in the same order as the causes, which are the button clicks, happen. So that's another thing. So just to summarize that, because that's kind of a mouthful, functional programmers explicitly manage the repetition and ordering of actions. This is one of those things I was talking about where functional programmers pay more attention to actions, that they know that the ordering and the repetition is really significant, so they are going to spend more time managing, like, what is the actual thing that I need to happen. All right, there's more in part 2. I just touched on 3 different things. We talk about functional tools. For each is a functional tool. It's basically functional tools, a basic way to put it is, maybe it's not perfectly correct, but it's clear and reusable for loops. We're talking about for each, map, filter, reduce. We develop each of those, and then we chain them together into data transformation pipelines. And this gives you a really concise way of working with data. Sometimes you have nested data, so you have like maps inside of maps, and we have some functional tools for dealing with those. We talked about some of these ways of controlling time. We develop a bunch of primitives. We developed one here, the only once. There's going to be more. We also talk about reactive models of state. So you have state that changes, and you want things to happen every time it changes so that the stuff stays up to date. And this is a way of turning cause and effect inside out. It's like another way that you can manipulate time. And then the onion architecture. This is a kind of a service level architectural system to structure your service into different layers. Okay, I'm at the end. Here's more about me. Again, my name is Eric Normand. My book is called Grokking Simplicity. You can find it at that link. I have a blog. I have a podcast all about functional programming and software design and the history of programming. Right now I'm reading Turing Award lectures, and commenting on them. I teach Clojure and functional programming. I have a newsletter, and I'm on Twitter. Wow, I do a lot of stuff. Okay, thank you very much. Here is, again, that coupon code if you want to get the book.